Hello friends, so today we are going to do the questions from the year 2015 and the total there are 6 questions, and in these 6 questions it is a combination of both mains as well as advanced. So first question, it was asked in the 2015 mains and it states that monochromatic light is incident on the glass prism of angle A. If the refractive index of the material of the prism is mu, a ray incident at an angle theta on the face AB would get transmitted through the face AC of the prism provided. So we have to find out which of this option is the correct one. Okay. And so here we are given a prism. So let's draw the approximate figure for that. And A is given as the angle of the prism, and we have a ray of light which is incident at an angle of theta, and it will be refracted to the other end, and let us suppose this angle of R1 and this angle of R2, and we have a, you can say, okay, so this is our A, B and C, and we have to find out the angle theta so that it can be transmitted through the face AC. Okay, so it will be coming as a emergent from the face AC, and the refractive index is given as mu. So we are given that angle of incidence on face AB, it is given as theta, and we have two refractive angles. One is along the face AB, and R2, basically it is an incident angle on the face AC, but still we represent it as R2 because the refraction when calculated with respect to AB. So we have two angles, R1 and R2. So we have this as angle of, let me write it separately. We have our angle of refraction inside prism at face AB. We have taken as R1, and we have angle of incident on face AC, angle of incidence on AC, that is also our, you can say, R2, and the angle of emergence, let us call that as theta 2, and we can say we have angle of emergence from AC, that is about theta 2, and from the prism relationship we know that our R1 plus R2 is equal to A. So from the prism we can say our R1 plus R2 is equal to A. Now it is said that the ray should be emerging from the face AC, and under this condition our R2 should be less than the critical angle, that is our theta C. Okay. So you can say for ray to emerge from AC, our R2 should be less than the critical angle. And critical angle we know is our sine inverse of 1 upon mu. This comes as sine inverse 1 upon mu. Therefore, we can write that our R2, which will equal to A minus R1, and it will be coming as less than sine inverse 1 upon mu. Or we can also say it that our R1 should be greater than A minus sine inverse 1 upon mu. Now we can use Snell's law at, let us suppose this we call as point P on the face AB. Snell's law at P on face AB, and we can write it as mu is equal to sine of theta divided by sine of our R1. Okay. Therefore, we can say manipulate the angles, and we can write it as that our R2 is equal to A minus, where we have sine inverse of sine of theta divided by mu should be less than sine inverse 1 upon mu. So we can write this as, because we are only interested in finding out theta, so we can straightforward write it as, we get this as, let me sort it out. So this becomes sine inverse sine of theta upon mu is equal to A minus, sorry, not equal to, but less than A minus sine inverse of 1 upon mu. Okay. So this sine inverse to the other side, it becomes sine. So this gives us that our sine of theta upon mu is less than sine of A minus sine inverse 1 upon mu. Now mu will be in multiplication, and therefore we can write our theta is less than, we have this as sine inverse, and this comes mu sine of A minus sine inverse 1 upon mu, and all the brackets closes. So this is our angle theta, and the option that is the correct one, you can say we have option number B is the correct one. Option B is correct. Next question. It was asked in the year 2015 advance, and it states that two identical glass rods S1 and S2, refractive index 1.5, have one convex end of radius of curvature 10 cm. They are placed with the curved surfaces at a distance d as shown in the figure, with their axes shown by dashed lines aligned. When a point source of light P is placed inside rod S1 on its axis at a distance of 50 cm from the curved surface, the light rays emanating from it are found to be parallel to the axis inside S2. The distance d is. So here we are given this figure. So we have two rods S1 and S2. They are having a common axis and a point source is placed inside S1, and it said that the point source, light rays from the point source in the rod S2 will be coming as a parallel one. So first of all, we can say the entire discussion can be carried out by analyzing two successive refraction. Okay. So one refraction will be along the curved surface of S1 and another one will be the curved surface of S2. So you can say we have two successive refractions. First one is at curved surface of S1, curved surface of S1, and the second one is at the curved surface of S2. Curved surface of S2. And there are some common parameters which are associated with both. Okay. So we can write that the radius of curvature for both is same. Radius of curvature for both is given as r and its value is 10 centimeter. The refractive index for both is also same. So we are given as a refractive index, that is our mu is our 1.5, and this is for glass, refractive index of glass, and obviously there is air associated with it also. So we can say refractive index of air, which is as usual is equal to 1. And we are given that the point object is inside S1 at a distance 50 centimeter. So we can say u with respect to S1 is our minus of 51. So u with respect to S1 is equal to minus of 50 centimeters. And we are also given that the final rays in S2 are parallel. So which means that the final image is at infinity. Final image is at infinity. So these are some parameters that are associated with. So we are going to consider the surfaces one by one and try to solve it. So first refraction is going to take place at S1. So you can say refraction at S1. Refraction at S1, and we can use the formula directly, and that formula is our N2 upon V minus N1 upon U is equal to N2 minus N1 upon R. So we substitute the value and we get this as 1 upon V, and this is minus 1.5 divided by minus of 50 is equal to 1 minus 1.5 and divide by minus of 10. So from here we get that our V is equal to 50 centimeters. Okay. That means the image from the first surface is formed at 50 centimeter in the air. Now this image is going to act as object for the second surface. You can say refraction at S2, and we can say that this image will act as object for S2, and the distance between the curve is given as d. Therefore we can write that u, so from here we can say that our u will be equal to it will be our d minus 50, and this will be minus of d, and image is at infinity, so v is our infinity, and here r will be equal to positive 10. So we are going to use same formula, and we get it as n2 upon v minus n1 upon u is equal to n2 minus n1 upon r. We substitute the values and we get this as, first term will be 0 minus, and n1 is our 1, this comes as minus d minus 50, and this is our, you can say 1.5 minus 1 and divide by 10. Okay. So therefore we get from here that our d is equal to 70 centimeters. So this was our option number B is the correct option. Option B is correct. Next question, and it is a passage based question which is having two sub questions to it, and in the passage it is given that light guidance in an optical fiber can be understood by considering a structure comprising of thin solid glass cylinder of refractance N1 surrounded by a medium of lower refractive index N2. The light guidance in the structure takes place due to successive total internal reflections at the interface of the media N1 and N2 as shown in the figure. All rays with the angle of incident I less than a particular value of Im is confined in the medium of refractive index N1. The numerical aperture of the structure is defined as sine of Im. Okay, so we are given this figure. So this is basic total internal reflection that is only explained here. So based on this we have two questions. In the first it says that for two structures, namely S1 having N1 as square root of 45 divided by 4 and N2 3 by 2, and S2 we have S1 8 by 4 and N2 7 by 4, taking the reference refractive index of the water to be 4 by 3 and that to the air to be 1, the correct option is or R. Okay. So here we are going to find out what will be the numerical aperture for each of the thing. Okay. And in the B part, second part, it is said that if two structures of the same cross-sectional area but different numerical apertures Na1 and Na2 are joined longitudinally, the numerical aperture of the combined structure is. In the first case, we are going to find out what will be the numerical aperture. Okay. So for that, let us draw a rough approximate figure with respect to the total internal reflection. And we have two surfaces, and refractive index is of n2, and here it is n1, and the incident ray, let us suppose it is incident at point P, making an angle of incidence as I, and it strikes the upper, you can say, surface at point Q, and obviously it will be total internal reflected, and in the vertical we say, let us suppose this angle as theta. So therefore we can write that this particular angle will be about 90 minus theta, and the surrounding one is, let us suppose, n0, refractive index. Therefore the total internal reflection will be, you can say, going to take place at Q if the angle of incident is greater than the critical angle. Okay, that is a basic premise of the our total internal reflection. So you can say that for total internal reflection, we should be having our theta should be either greater than or equal to the critical angle, that is theta c, and this comes as sine inverse of n2 by n1. Okay. And we are going to use the Snell's law at point P. Snell's law at P, we can write it as n0 sine of I is equal to n1, and this is sine of 90 minus theta. So we can just, sine of 90 minus theta is cos theta, so we can write this as our n0 sine of I is equal to n1 cos of theta, and cos of theta we can write in terms of sine as 1 minus sine square theta. And we can say that if angle of the incident is maximum, that is equal to I is equal to Im, and we are going to get that when theta is the minimum, that is theta is equal to theta c. So we can write the equation for the numerical aperture, which is also given in the question also. The numerical aperture is given as sine of Im, and Im is a particular value of angle of incident, that is given as Im, and basically it says that it is with respect to the is confined total internal reflection. Okay, so Im is with respect to the total internal reflection. Therefore we can write that our numerical aperture, which is equal to sine of Im, and this we can write as, if we substitute it in this particular equation, let us put this as equation 1. Okay. So we can write this as n1 square root of 1 minus sine square theta c and divided by n0. Okay, and here we have to remember that the angle of incident is maximum, you can say at I is equal to Im, that is the maximum intensity, maximum incidence angle. So you can say when theta is our minimum, that is we have our theta is equal to theta c. So this is the only manipulation we made in the given equation. And we already know value of our, or we can just further solve it, because sine of theta c is our n2 by n1. Okay, so we substitute it here and we get this at that our numerical aperture will be equal to our n1 minus n1 square root of 1 minus, and this comes as n2 upon n1 square and n1 square and divided by n0. We take n1 as LCM along with common, n1 goes with n1, so we are left with only part, that is our n1 square minus n2 square and divided by n0. And we already know the value of n1 and n2 is given to us. We are given that n1 is our square root of 45 divided by 4, and value of n2 is given as 3 by 2. And based on this, we can find out numerical aperture 1, and that will be equal to, we have this as 45 upon 16 minus, this is comes as 9 upon 4, and it's square root, and this is our n0. So it comes as 3 upon 4 times n0. So this is a numerical aperture 1. Similarly, we can find out numerical aperture 2. For the second part, we are given that our n1 is equal to 8 by 4 and our n2 is given as 7 by 5. So similarly, we get our n2 numerical aperture 2 will be equal to 64 divided by 16 minus, and this is 49 divided by 25. Okay, this is 8 by 4. 8 by 5, sorry. Otherwise it would have very complicated solution. So we get this as 25 and its square root divided by n0. So this gives us, this comes 5, and we have square root of 15 divided by 5 times n0. Okay. Now we are going to discuss the options one by one by considering these two numerical aperture, Na1 and Na2 as well, because only difference between the two is the value of n0. Okay, and n0 will be decided by, you can say, their respective immersed refractive indexes, because n0 is the surrounding refractive index. Okay, that will depending upon in which liquid it is immersed. So we have option A, and option A we are given that value of n0 is our 4 by 3. Okay. Therefore, we get our Na1 will be equal to, this is our 3 by 4 multiplied by 4 by 3. This comes as 9 upon 16, and we substitute our n0, that is given as 16 divided by 3 multiplied by 15. 16 divided by 3 multiplied by 15, and from here we get our Na2 will be equal to, we have here 15 and this is about 5 divided by 16, and this comes as square root of 15. So we get our Na2 will be equal to 9 upon 16. Okay. Now we have option B. In option B, we are given that our n0 is equal to 6 upon square root of 15. Okay. So this gives us that our Na1 will be equal to Na1, okay, 3 by 4 N naught. 3 by 4 multiplied by 6 divided by 15. So this gives us that our Na1 will be equal to square root of 15 and divided by 8. And other value of N naught that is given to us is our 4 by 3. So this gives us that our Na2 is equal to, and we have this as square root of 15, 5, and this comes as 4 and 3. So this comes as 3 square root of 15 divided by 20. Now we come to the option C. Option C, we are given that N naught is equal to 1. So therefore our Na1 will be equal to 3 by 4. And for the second, we are given that our N naught is 4 upon square root of 15. So this gives us that our Na2, which was equal to 15 by 5, square root of 15 by 5, and this is our 4 by 15 square root. So we get our Na2 will be equal to 3 by 4. And finally, option D. And option D, we get this as our N naught is equal to 1. So here Na1 will be equal to 3 by 4, and N naught is given to us, I hope it's written correctly, 3 by 4. And second case, N naught is given as 4 by 3. Yeah, now it's correct. So we get our Na2 will be equal to, this comes as 3 square root of 15 divided by 20. And so if you check the options, the option number is, it states that numerical aperture of S1 immersed in water is same that of S2. Okay, we have to check the numerical apertures for all the options, and I think option A is, I think, correct one, and option B is not correct, and we have option C is also correct, and option D is incorrect. So we have option C, option A and C are correct. So we have A and C are both correct. So we have option A and C are correct. And in the second part, it says about if we join two structure of same cross-sectional area are joined together. Okay, so we have to find out what will be their combined numerical aperture. And for option B, okay, we already know that, so part 2, we already know that sine of Im is equal to N1, and this is sine of 90 minus theta C, or total internal reflection. So we get from here that sine of Im is equal to N1 cos of theta C. So from here we get our numerical aperture is equal to N1 square root of 1 minus sine square theta C, and sine of critical angle we already know. So we can write that the numerical aperture is equal to this will be n1, and 1 minus this we get n2 square and n1 square. N1 take LCM and it's common, so this gives us that square root of n1 square and minus n2 square. And I think I missed something. It doesn't look. Let me check. Let me solve this first one, then we'll check it again. And we have our n11 is equal to 3 by 4, and we have our n2 is equal to square root of 15 divided by 5. And what is missing? So this comes as square root of, I think something is missing here. 1 second, let me check it again. So we are given a light guidance in an object. Okay, yeah, this one. I think I sorted out. So I think this is wrong. Okay, I have to. Okay. So in this part, we are given that the numerical aperture of 2 is less than numerical aperture of 1. So we start from there only. So we are given that numerical aperture of 2 will be less than numerical aperture of 1. So therefore we can say that our IM2 will be less than our IM1. It means if the combination is placed, because it is said that it is connected one after another, so the combination can be placed in 2 ways. Okay. So combination can be placed in 2 ways. In the first way, we have structure 1 and then we have structure 2. And the second one is structure 2 we are going to have first, and then we are going to have structure 1. And under this you can say both the conditions. You can say the condition for total internal reflection, you can say for both total internal reflection is satisfied for lower IM, then it can be satisfied for all other lesser angle as well. Because if the condition for total total internal reflection is satisfied for this value, then the any value which is less than IM will be also automatically satisfying the total internal reflection condition. Okay. So you can say then it can be satisfied for all other angles less than IM. So we can say that our Na2 will be the numerical aperture of the combined structure, will be the numerical aperture, let me write it, Na in the shorter form will be our numerical aperture for combined structure. So the option number D, yeah, is the correct one. Option D is correct. Okay. So we come to the next question, and in the next question it is given that we have a it was asked in the 2015 advance, and it states that consider a concave mirror and a convex lens refractive index 1.5 of a focal length 10 cm each, separated by a distance of 50 cm in air, a refractive index 1, as shown in the figure. An object is placed at a distance of 15 cm from the mirror. Its erect image formed by the combination has a magnification m1. When the setup is kept in a medium of refractive index 7/6, the magnification becomes m2. Then the magnitude of m1 by m2 is. So this is, you can say, this question can be divided into two refractive indexes, and one is when they are in air and another one is when they are kept in a medium. Okay, so we have two mediums, refractive index 7/6, and we have a refractive index of 1, that is of air. So we have two, one is mirror and another one is our lens. So let us start for mirror, and this is for air. So you can say for mirror, we have u is equal to minus of 15, the focal length will be equal to 10. So we can use the formula 1 upon v, 1 upon v plus 1 upon u is equal to 1 upon f. We substitute, we get this as 1 upon v, and this comes with plus minus of 15 is equal to minus 1 upon 10, and this gives us that our v is equal to minus of 30, and we can find out here m1 will be equal to, that is minus v upon u, so it comes minus of, this is a minus of 30 and this is minus of 15, this gives us 2, minus of 2, and it means the first image is formed at a 30 centimeter from the mirror. Now this is going to behave as an object for the lens. So you can see this image will behave like a object for lens, and for lens we have u is equal to minus of 20 and the focal length is our 10. Therefore, we can write that 1 upon v minus 1 upon u is equal to 1 upon f. We substitute the values. 1 upon v minus of minus 20 is equal to 1 upon 10. So this gives us that v is equal to 20. Similarly, we can find out here m2. This m2 is our 20 upon minus of 20. This gives us minus of 1. So the total magnification which is given as capital M1 will be equal to small m1 to m2, that comes as 2 into minus 1, and we get our m1 is equal to 2. Now we have a second medium that is given as second medium is refractive index 7/6. So you can say for medium whose mu is given as 7/6. Therefore, we can write that for our mirror, we can write that our 1 upon f is equal to mu minus 1, and this comes as 1 and r by 2. And we substitute the values. We get this as 1 upon 10 is equal to, we have this as, one second, let me check if it's something wrong. Looks good. And we have this as 1/10, and the refractive index is given as 3/2 minus, and we get this as 1 upon r1 minus 1 upon r2. So from here we get this as 1 upon r1 minus 1 upon r2 will be equal to 1 upon 5. And for the medium, that is given as mu is equal to 7/6. So we can write that as mu is equal to 7/6. So this gives us, let us suppose f prime is equal to, and now we have 3/2 and 7/6 minus 1, and this comes as 1 upon r1 minus 1 upon r2. And from here, r1 and 1 upon r2 we just found out is 1 upon 5. So this comes as 2 upon 7 multiplied by 1/5. So we get that our f prime rather is equal to, this will be equal to our 35/2. Okay. And one second. Okay, now we are, this was for our lens. This was for our lens, and the first part is, we got our f prime, and for mirror there will be no change. You can see for mirror there will be no change, and which means that our u is equal to minus of 15 f will be equal to minus of 10 and our v is equal to minus of 30 and our m1 is equal to minus of 2. And for length we have our u is equal to minus of 20 and f is equal to 35 by 2, that is our f prime. So therefore we can write that 1 upon v minus 1 upon u is equal to 1 upon f prime in this case, and we substitute the values, we get 1 upon v minus of minus 20 and this is equal to over 2 upon 35. This gives that v will be equal to 140. So therefore we can write our m2 will be equal to 140 upon minus of 20, giving us minus of 7. And therefore the capital M2 will be equal to small m1 multiplied by m2, and that will equal to minus of 7 multiplied by minus of 2, that is over 14. And we have to going to find out the ratio now. We have the m2 upon m1 is equal to 14 by 2 and that comes as 7. Okay, so it was m1 by m2. Yeah, it was m1 by m2. Let me reverse it. So we have m1 upon m2 is equal to 1 upon 7. So we come to the next question. It was also asked in the year 2015 advance, and it states that a Young's double slit interference arrangement with slit S1 in air and S2 is immersed in water, refractive index 4 by 3 as shown in figure. The position of maxima on the surface of water are given by x square is equal to p square m square lambda square minus d square, where lambda is the wavelength of the light in the air and 2d is the separation between the slits and m is an integer. The value of p is. So we can say distance is given between the two is given as d and this is our x. So we can easily say that the distance between this two will be our square root of x square plus d square, and other one will be also x square plus d square. And for maxima, the path difference should be equal to m times lambda. So we start from there only. So we say for maxima, path difference is equal to m times lambda. So let us call this as point A, and so we can write it as S2A minus S1A is equal to m times lambda. And here one of the path, that is our S2A, is within the water. So therefore we can write it as our n minus 1 and square root of d square plus x square, and this comes as plus d square plus x square square root and minus square root of d square minus x square is equal to m times lambda. And this is quite easy to solve now. So we get here from n minus 1 and this comes at d square plus x square is equal to m times lambda, and we substitute value of n, that is refractive index, we get this as 4 by 3 minus 1 square root of d square plus x square is equal to m times lambda, and this can be written as d square plus x square and its square root is equal to 3m times lambda. So we can just, you can say, rearrange this equation as per the equation given in the question. Okay, so we are going to rearrange it, and this gives us that our x square is equal to 9m square lambda square minus d square. So therefore we get our p square is equal to 9, giving us p is equal to 3. So we come to the next question. It was also asked in the 2015 advance, and it states that a monochromatic beam of light is incident at 60 degree on one face of an equilateral prism of refractive index n and emerges from the opposite face, making an angle of theta n with the normal as in figure. For n is equal to square root of 3, the value of theta is our 60 degree, and derivative of theta with respect to n is given as m. Then the value of m is. So here we are given that the theta is an angle which is dependent upon the refractive index, where n is the refractive index and theta is the angle. So here the theta is a, you can say, function. Here it is as an angle which is dependent upon n. Okay. And it's an equilateral triangle. So the prism angle, that is our A, will be equal to 60 degree. Okay. And the angle of incident for n is equal to square root of 3, it is given as 60 degree. And therefore we can say that our, for equilateral triangle, for equilateral prism rather, equilateral prism, we have our angle A is equal to 60 degree, and we are also given that for n is equal to square root of 3, we are given that angle of incident, let us suppose that our I1 is equal to 60 degree. Okay. And let this angle be the angle of refraction, that is of R1. So let this point as P. So using Snell's law at point P. Snell's law at P. So we have here, that is our 1, and we have this as sine of I1 is equal to n and sine of R1. So I1 is our 60. So we get this as sine of 60, n is our n, and this comes as sine of R1. Sine of 60 is our square root of 3. So we can write this as square root of 3 by 2, sorry, is equal to n, and we have sine of R1. So therefore we get that sine of R1 is equal to square root of 3 divided by 2n. And for the ray which is inside the prism, and let us suppose we have a second angle, that let us call as R2. So from the triangle prism property, R1 plus R2 is equal to A. We can say that our R1 plus R2 is equal to A. So from here we can write that our R2 is equal to A minus R1, and which comes as 60 minus R1. Now we apply the Snell's law at the second surface, and that is point Q. Okay, Snell's law at Q. And here we have n times sine of R2 is equal to 1 multiplied by sine of theta, and we substitute our R2, which is 60 minus R1. So we get n, and sine of 60 minus r1 is equal to sine of theta, and sine of our r1 we already know is our square root of 3 divided by 2n. So from here let us calculate our r1. r1 is our sine inverse square root of 3 divided by 2n. So therefore we can write the equation that our theta n, which is here theta, depending upon refractive index, this will be coming as sine inverse, and we have here n sine of 60 minus, and r1 is our sine inverse of square root of 3 divided by n. Sine inverse square root of 3 divided by 2n. Okay, so this is value of theta n, and we are given that the derivative of theta with respect to n is equal to m. So we just derivate it, and for the sake of convenience let us say that let our theta n is equal to sine inverse of a function which is our n function. So if we derivate it, we get this as derivative of theta n divided by n is equal to, become this as 1 upon 1 minus function of n and its square as well as square root, and coming as df upon dn. And we are given that value of n is equal to square root of 3 when theta is equal to 60. Okay. And theta is equal to 60. So we can say that our sine of theta will be equal to square root of 3 divided by 2. So we can find out our function, that is our f of n will be equal to square root of 3 divided by 2, and from here we can write 1 upon function of n, that is whole square and its square root. This will be coming as 1 minus square root of 3 divided by 2 and its whole square and square root, and this will be coming as equal to 1 by 2. And now we are going to calculate our df by dn at n is equal to square root of 3. Okay. So our f of n was our n, and here we have sine of 60 minus sine inverse of square root of 3 divided by 2n. And let us assume that let our x is equal to sine inverse of square root of 3 divided by 2n. So this simplifies our function that of n is equal to n sine of 60 minus x. Now we can derivate it. So we get derivative of f divided for n is equal to, this will be a sine of 60 minus x plus n, and we get a cos of 60 minus x and minus of dx with respect to dn. And we are given, or we just, this is our x, so we can differentiate it, and this is going to give us that our dx upon dn is equal to d of dn, and here we have sine inverse of square root of 3 divided by 2n, and this simplifies at minus of square root of 3 divided by 2n square and square root of 1 minus square root of 3 divided by 2n and its whole square. Okay. And for n is equal to square root of 3. For n is equal to square root of 3. So let us calculate first of all this part, and we get this as square root of 3 divided by 2n is equal to square root of 3 divided by 2 multiplied by square root of 3. This gives us 1 by 2. And we can say that our x, which is our sine inverse of 1 by 2, and this gives us 30. And we also require 60 minus x, which will be also coming as 30. And we know that sine of 30 is 1 by 2 and cos of 30 is square root of 3 by 2. And we know that sine of 30 is equal to 1 by 2, and we have cos of 30, which is equal to square root of 3 divided by 2. We have done most of the calculations now. So we find out our dx upon dn will be equal to minus square root of 3 and divided by 2n square. 1 minus, we just found out that square root of is 1 by 4, and its square root, and this gives us that minus square root of 3, we have 2n square, and this will be over 4 minus 1, that is square root of 3 divided by 2. So here square root of 3, square root of 2 and 2 goes away, so we are left with this as 1 upon n square. Now we can substitute everything in this particular equation. So we get df upon dn is equal to sine of 30 plus n cos of 30, and we got this as 1 upon n square. Okay, if I'm correct. Yeah, minus was there, so this becomes plus 1 upon n square. And cos of 30, sine of 30 value we already know. Sine of 30 is our 1 by 2 plus n, and this comes as square root of 3 divided by 2 multiplied by 1 upon n square. And here this square cancel this n, and we get this is equal to 1 upon 2 plus square root of 3 divided by 2n. So we found out df upon dn. Let me name the equation, it is getting confusions. Okay, let's suppose this is our equation number 1 and this is our equation number 2. Okay. Therefore, here we use equation 2. From equation 2, now we are going to use equation 1. From equation 1, which is our ultimate aim, finding d theta by dn. So d theta by dn, which is equal to 1 upon 1 minus function of n and its whole square root divided by df upon dn. And we simply plug in the values. We get this as 1 upon 1 by 2, and df by dn is our 1 by 2 plus square root of 3 and divided by 2n. Okay, so 2 goes on the top, so this 2 and this 2 cancels out, and we get this as d theta by dn is equal to 1 plus square root of 3 divided by n. And finally, we know that n is square root of 3. So therefore, d theta by dn is equal to 1 plus square root of 3 divided by square root of 3. Cancels out. This comes as 1 plus 1, which is giving us 2. Okay, anything else? Yeah, the value of m is equal to, because d theta by dn is given as m. So value of m is equal to 2. You can say this is equal to m. So the question was, calculation wise was quite lengthy. Otherwise, there is a simple application of Snell's law. Okay, so only thing that we have to remember, that taking the derivatives multiple times. So it is a little bit lengthy to solve. I think this completes all the questions. Yeah, so these were the questions which were asked in the 2015 mains and advance. These completes all the questions. Thank you.